Every single time you stream a movie or jump on a video call or even just browse the web, you are tapping into this invisible nervous system that wraps around our entire planet. It's this incredible network made not of copper, but of pure light, shooting through tiny threads of glass. This is the story of fiber optics.
But that raises a question that seems to kind of defy common sense, right? How in the world can you send light through a solid piece of glass and make it go around a corner? It's like piping light, as if it were water. Well, this is the central magic trick of fiber optics, and the answer lies in a really brilliant physics principle that turns glass into a perfect tunnel for light.
Okay, so an optical fiber isn't just one uniform piece of glass. It actually has two parts. There's a central core, and then wrapped all around it is a layer called the cladding. Now, the whole secret is that these two layers are engineered to handle light in very, very different ways, and that creates this special boundary right between them.
And the principle that makes it all work is called total internal reflection. It sounds complicated, but it's not. Because the core is optically denser than the cladding, when light inside the core tries to escape at a really shallow angle, it just can't. It hits that boundary and bounces perfectly back into the core, almost like it's hitting a flawless mirror, over and over and over again.
So by turning the boundary between two types of glass into what is essentially a perfect light tunnel, you can trap a beam of light and guide it literally wherever the fiber goes. And that simple, elegant principle, that's the whole key.
But here's the thing. The idea of guiding light is much, much older than the internet. I mean, scientists and inventors have been playing around with this concept for over 2 centuries, way before they could even dream of sending data at the speed of light.
And what's really fascinating is just how creative these early attempts were. We're talking about tower-based telegraphs way back in the 1790s. John Tyndall's famous 1854 demonstration where he made light follow a curving stream of water. And even Alexander Graham Bell had something called a photophone. By the 1880s, doctors were even using bent glass rods to see inside the human body. The dream was definitely there.
But a dream is not a global communications network. To get from a cool little science demonstration to streaming 4K video across an ocean, technology needed 3 absolutely monumental breakthroughs.
So here they are. First, you needed a pure, concentrated light source, which we got with the invention of the laser. Second, you needed an ultra-clear pipe. That's the low-loss glass fiber to carry the signal without it just fading away. And third, you needed a powerful way to boost that signal for the really long hauls, and that was the optical amplifier.
Now, that second step, the glass itself, that was the biggest hurdle. Early fibers were just so full of tiny impurities that the light signal died out almost instantly. So the challenge was taken up by researchers at Corning Glassworks. And their goal? Well, it was to create a type of glass so unbelievably pure that it was actually more transparent than air.
And this was the magic number. In 1970, the team at Corning finally achieved an attenuation, that's just a fancy word for signal loss, of less than 20 decibels per kilometer. For the very first time, light could travel far enough through glass to make a global network actually feasible. This was the moment that proved fiber optic communication wasn't just possible, it was going to be a commercial reality.
And then, the final piece of the puzzle fell into place in 1986. This was the erbium-doped fiber amplifier. It could boost the light signal directly, without the really clunky, expensive step of converting it to electricity and then back to light again. This is what made sending cables across entire oceans truly practical.
So, with all 3 breakthroughs finally in place, the race was on. In just a couple of decades, humanity undertook one of the greatest infrastructure projects in history, wrapping the entire world in these tiny threads of glass.
And the pace was just incredible. I mean, think about it. From the first phone calls in 1977 to the first cable across the Atlantic in '88, and then by 1997 you had the fiber optic link around the globe, which laid the very groundwork that would fuel the whole .com boom. But it turns out, not all fiber is created equal. The early multi-mode fibers had a pretty wide core, which let light rays take a bunch of different paths, kind of like cars in multiple lanes on a highway. So you see how the red ray takes a longer zigzag path than the blue one? Well, that means parts of the signal arrive at different times, which basically smears the data. This effect is called dispersion, and it was a huge roadblock for speed and distance.
So a really clever solution was this graded index fiber. Think of it like a racetrack with a banked curve. The glass in the core is engineered to actually make the light rays traveling on those longer outer paths go a little bit faster. This helps all the light, whether it took the red path or the blue path, arrive at the finish line at roughly the same time. It was a huge improvement.
But the ultimate champion, The real hero of the story is single-mode fiber. For this one, the core is made incredibly thin. We're talking just a few microns across. And that forces all the light down a single express lane. There are no other paths to take. This completely gets rid of that signal smearing, which allows for the absolutely mind-boggling speeds and distances that power our modern world.
So, when you put it all together, what does it really mean for us, today? Well, it means this. This technology has basically given us superpowers that have completely reshaped society. I mean, just think about it. Massive bandwidth? That means smooth 4K streaming for millions of people all at once. It's immunity to interference? That's why your video call doesn't glitch out during a thunderstorm. It's also incredibly secure, and because it can carry a signal for over 100 kilometers without needing a boost, it's super efficient. And the best part? It's all made from sand. It is pretty much a perfect communication medium.
Oh, and what about all those stories of sharks eating the internet? Well, while there have been a few cases of sharks biting undersea cables, it's incredibly rare. The folklore has just gotten way bigger than the reality. The cables are actually quite safe from marine life.
You know, this quote really just sums it all up perfectly. As our demand for information just exploded, we needed a new kind of pipe to carry it all. Fiber optics wasn't just an option, it was and it still is the solution.
So, we've wrapped our entire world in this incredible web of light, an achievement built on more than a century of curiosity and genius. And the thing is, the capacity of this network is still almost limitless. So the only real question left is, what are we going to dream up to do with it next?